All right, welcome back everyone. We are ready to continue our exploration of the type support in PostgreSQL. In this video, we will look at two things actually, but they are related. It's about storing sequences of bits inside PostgreSQL. Bit sequences that PostgreSQL itself will not interpret or try to operate on, but it will plainly keep these bit sequences for us so that we can later reproduce them for the display of images or the playing of sound files or whatever you have. All right, so it's about bit data inside PostgreSQL. The first bit, pun intended, I'm going to show you here is the storage of short bit strings. And PostgreSQL has a dedicated type to do to perform storage of such short bit strings. It's called byte, which would represent a sequence of n bits stored really compactly and efficiently. So n binary digits are stored in the expected 1 byte stores 8-bit format. Such a value of type byte will have some constant and small overhead, but normally you would expect 1 byte being invested to store 8 bits of your bit sequence. So how would you specify literals or literal bit strings, constant bit strings in your queries? There's multiple options to do that. One option that's really readable is this variant in which you have a prefixed b in front of a literal bit string, just consisting of 0 and 1 characters. There's also a variant where you can use the hexadecimal notation, using the leading X here in this place, and then having a string of hexadecimal digits in which each of the hexadecimal digits represents 4 bits, a nibble, as some people would say. So this is the hexadecimal representation of the decimal value 42 using 2 decimal digits. All right. There's also the expected casting notation, so we can cast from this literal textual bit string using this cast notation into a bit, internal bit string of 8 bits, say. And we can also convert decimal values and other numeric values into bit strings using this casting notation. All right, so this is how we would specify bit string literals. Once we have them, we can perform the expected operations on these. So we have the operations of the Boolean algebra and can perform the AND and the OR operation. There's XOR operations or negation. All right, we can do all kinds of shifting. We can inquire particular bits. Is a particular bit in a bit string, bit sequence set? We can generate new bit sequences in that we modify and set a particular bit to 0 or 1 at a particular position in a bit sequence. And then, because we are talking about sequences of bits, you also find operations that are string-like in PostgreSQL. So you can concatenate such bit sequences. You can inquire the length. So how many bits are actually stored in such a sequence? This is the length and the bit length operations, but there's also the octet length operation that we've already discussed as we were talking about textual data. And with octet length, you can inquire how many bytes are actually used to store the bits in your bit sequence. All right. What you can also do is you can look for bit patterns inside a longer bit string. So you can check where and if a particular sequence of bits occurs in a larger bit string that you are specifying here in the position function. Okay, so all of this would be support for rather small bit sequences that you can explicitly write down and embed as literals in your queries. The other bit I wanted to tell you is about binary data inside PostgreSQL that is really considerably larger than just a few bits that we've just described. I'm talking about binary arrays or binary large object blocks or BLOBS. Okay, In such a binary large object blob, you can store anything you like. PostgreSQL will not look inside these binary large object blocks and try to interpret their the contents in any way. It does not have to fit any particular format. It's just a sequence of bytes that is kept for you safe inside the table by Postgres, and that you can then query and reproduce just like any other data that you've stored in your database. All right, so this would be the way to capture images, for example, or sounds. And I brought an example with me that will show you the use of sound data inside PostgreSQL. All right. How we store such blobs inside PostgreSQL is simply by using a particular type, the bytea or byte array type inside PostgreSQL, and have that as the column type of one column in your table, or one or multiple columns in your table. In this case, in this example, it would be the column B, the middle column of the sample table T here. Okay, and as you can see, as I tried to indicate here, this would be the byte array, the binary string representation of your images or other multimedia files or any other data really that you want to store inside PostgreSQL. To retrieve this data meaningfully, it's normally custom to accompany such binary data by key fields that we can use in queries to identify a particular row of such a table T. So we would not look for particular binary patterns inside the binary large object blocks that we've stored here themselves, but we would rather use additional keys to locate particular image files, to locate particular binary object that we've stored. Okay. Other properties, metadata properties like the length of a sound file, the X and Y dimensions of an image, and so on, would probably be better stored inside explicit property columns indicated by the sample column P here in this case. So you would use these additional key columns to locate a particular row in this table together with the embedded byte array, the binary large object block. You would then check the property columns, of which there could be many, any that you want, to check details, metadata about the binary large object that you have stored in this particular row, and then you could just extract parts or all of the binary data array that has been stored inside this row for further use in external tools or maybe even inside your queries. Just remember that PostgreSQL will never try to interpret the contents of these byte arrays. Okay, so a typical setup and of how you would bring such data inside PostgreSQL and then really extract it again from a PostgreSQL table would be the following. So our target would be to construct a table with such a byte A column, such a column B here. Inside this column, we want to store byte array data or binary large object blocks. Externally to the database system, we will probably have files in which these binary data are stored. And there are functions provided by PostgreSQL, for example, the large object import function or the LO import function, or functions like read blob, which I've designed myself and which you will find in the sample file that we are going to discuss in a minute. Such functions could be used to directly read the external binary data files from your file system and then import the data directly and into the table and place it in the byte array column of your table. This would be the direct way to ingest binary data from your file system. Another way, one that we will also discuss in an example in a minute, would be using an intermediate step by first encoding the binary file data into some textual format that is easily handled and that can be easily passed from tool to tool in a Unix world. For example, by using base64 encoding, to turn this binary data into a textual form, a textual gibberish long string that we could handle with other tools or even inside PostgreSQL. If we have such a large string inside PostgreSQL, we could use the built-in decode function. So place that large character string as a first argument in this decode function, inform the decode function that this binary data has been encoded, textually encoded by the base 64 standard, and then decode the bits, the bytes of your binary file into a form that can then be directly placed into the bytea column. Okay, and the way out of this table back into the form of binary data that could be then fed to other tools, image manipulation programs or sound playing files programs, for example, would be to take this byte array data, encode it into base 64 form. What we would get is this textual representation, which would then be passed from tool to tool, maybe passed inside the queries that you're writing in PostgreSQL. And once you're ready to really externalize the binary data and pass it on to some external consumer, your program or some other external media consuming program, you would then use a base 64 decoder to turn this textual representation into binary data again. All right, so either the direct way or the intermediate step through a textual representation, for example, base 64, to better handle such text strings with your applications or inside the database system. Also for display, this is really convenient, and we will see this in a second. Okay, so let's switch over. Let's switch over to the editor, and there we are. All right. So what I'm trying to do in this example is to ingest binary data into PostgreSQL and store it in a table. Okay, and we will save this binary data inside this table GLaDOS. It's named like this because the binary data that we're going to store will be sound samples, WAV samples of the GLaDOS main villain, let's say, in the Portal 1 and 2 computer games. You may not know these, or you may know these. If you don't know these, Google for Portal 1 and 2, Google for GLaDOS, and do yourself a favor and play these fantastic games. All right, you have been warned, it's a time sink. Okay, so what we will do is to store GLaDOS sound samples inside PostgreSQL, and we will do this in this 4-column table. One of the columns, the first column here, is a dedicated key column that we will use to identify a particular sound file, GLaDOS sound file, that we are holding in this table here. Okay, so we will not use the binary data itself to identify itself. We will use an external extra key that is easily indexed and looked up for using where clauses in a SQL query. We will also add additional metadata to the sound sample. For example, an excerpt of the text that is actually spoken by GLaDOS, or maybe the addition of the game in which this particular line was spoken by GLaDOS. And you can see that I'm making use of a user-defined enumerated type here called edition, which only has 2 admissible values, Portal 1 and Portal 2. It's a pity, but there are only 2 games in the Portal series until now. All right. The second column is where we will really store the binary data. In this byte array column, we will have the column voice, which will be the blob, the binary large object in which we will hold the sound samples. Okay, so let's set up the GLaDOS table. First, let's have the user-defined enumeration type defined, and let's have the table defined. There you go. All right. Okay, so now it's time to really ingest the data, and the data is currently stored in my file system. This is the directory in which the files will be stored. This is the insert query. So we will insert, as you can see, 4 lines, 4 GLaDOS sound samples. And here you can see how I have prepared a literal table that I will use to prepare my GLaDOS table. So we are providing the keys 1, 2, 3, 4 here, we will be providing metadata, for example, the textual representation of what's being said in a sample and from which game we have taken these samples. All right. And these are parts of the base names of the files in which the WAV files are actually placed. So let's switch over to my terminal here and look inside the indicated directory in my file system. There are indeed 4 WAV files. We will import these 4 WAV files into PostgreSQL, and you can see that these are really binary large objects. So they are about 800K or maybe 350K. So these are really sizable binary objects that we don't want to represent in the bit n syntax, for example. Okay. So rather what we're doing, we are inserting these 4 lines into the GLaDOS table by just simply copying the portal, the primary key information and also the metadata. So these two fields are the metadata that we are going to insert. And here in the last column, the voice column, I will use the read blob function, that I've mentioned in the slide that we were just discussing. The read blob function will directly ingest from the file system. This is the file system path I'm going to be using. It's a concatenation of the directory I've specified above and the base name of the WAV file that we are reading off this literary table. So this file will be used to look up in the file system the WAV file and then use the read blob function. You will see and can inspect the read blob function once you download the glados.sql file from GitHub. The read blob function will ingest the file and place it inside the byte array column inside my table GLaDOS. And if we look at the signature at the type of the read blob function, it's exactly what you would expect. This read blob function reads, gets a file name, the blob file name, this is what we get here, and it emits a byte array, a binary large object block, something suitable that we can directly place in the voice column of our GLaDOS table. Okay, so let's just do that here. Okay, so ingested. The binary WAV data is now inside PostgreSQL. To really check that and to see that we have really imported all this binary data, let's look at the current state of the GLaDOS table. So we are iterating over the rows of the GLaDOS table. We are printing the key information and all the meta information. And we also check the voice column, which holds the binary large object block. But we will not print that large binary object block onto the terminal here. We will first encode it into base64 form. So the binary data will be transformed into some textual format, as also mentioned on the slide before. And the textual format will be huge, will be humongous. So we are content with only seeing the first 20 characters of this textual representation of the binary data to check that the import went okay. So let's do this. All right, there you go. 4 lines have been ingested with key data and metadata, and here you can see the first few 20 characters of the text representation of the WAV files. They look similar, but if you look more closely, you will see that they are indeed different. We have indeed stored the different WAV files inside the GLaDOS table. All right, so that's half of the story. We have stored stuff. We will be able to extract and reproduce stuff, of course, so that somebody else, probably some external program, can get hold of the binary data again and do its thing, like play sound, for example. And that's what we are doing here. We are just formulating a typical select from where query. So we extract from the GLaDOS table one particular row, one particular sample, and as you can see, I'm using the key information. I could also use the property, the metadata information that I've stored in the table, but I'm using the key information here to extract the sample with key ID 3. All right, once I got hold of this, I will again encode this into textual format using this built-in encode function. So what I will get here is the textual format, the base 64 format of the sound sample. I'm cleaning that up here, so let's not talk about this here, but I'm cleaning up the textual format, ready to be passed into a base 64 decoder that I have on my computer here. So what you can see here is some PostgreSQL functionality that you will find in every SQL database system. It's one way to take the result of a particular query and then pass that result on to an external program. And this is the copy to program syntax I'm using here. The extracted base 64 data is passed to an external program, a base 64 decoder, which will leave the decoded WAV sample in this particular file in the file system. All right. Okay, so let's do that. Let's extract the sound sample with ID equals 3. ID equals 3 is something that is corresponding to a facility that GLaDOS is talking about. So let's do that. All right, extract. Okay, query executed, and the copy 1 indicates that this query result had actually been passed into this external program, the base 64 decoder. Okay, so let's switch back to the terminal here, and let's check that the GLaDOS WAV file has actually been created. And as you can see, May 5th, 1150, this is the current time. Okay, and we've extracted 354,896 bytes. This is exactly what we've ingested. So that's what we expected, that no bit has been lost or been appended to the binary data. The binary data has been reproduced faithfully. And let's check if this is the case. We can just play the sound sample here. Let's see what GLaDOS has to say.
That's right. The facility is completely operational again.
All right. Good for you, GLaDOS. Let's extract something else. Let's extract the second sample here. Run the query again. Done. Okay. And play the sample again.
You think you're doing some damage?
2 plus 2 is
10. In base 4, I'm fine.
All right, GLaDOS, you're fine. I'm getting it. Okay. This, by the way, was even a binary inclined joke by GLaDOS. That's fitting very nicely. Okay, so that's about it. That's the import and the reproduction of binary large object blocks of byte arrays using the bytea type inside PostgreSQL. This is considerably different to the small bit sequences that I can type in literally in my SQL queries that I've shown you in the first few minutes of the video, but these are two methods to store binary data inside PostgreSQL. There's more to be said regarding types in PostgreSQL, but not in this video. See you again in the upcoming videos. Until then, bye.